Welcome back to part 2 of our tutorial on how to build a Tetris game in Scratch. So last time out we learned how to randomly generate blocks and have them fall down the screen. When they hit the bottom, we use an ingenious color coding and stamping technique to turn the sprites into images that we'll later on be able to manipulate. So this week we're going to take it to the next step where we're able to take these individual rows of blocks and delete certain rows and have the blocks on top of them fall down a level. And that's an important component of any Tetris game, of course. We're also going to learn how to use keyboard commands to move the blocks left and right and rotate them as they're falling so that we can get them into the right position. All that and more coming right up. So I'm inside the file that we started working on last week. I'm going to resave this and call it Tetris Part 1 Catch-Up File. And so if you're starting right now at Part 2, you'll be able to follow the link in the description and get to where we are right now so you can start coding at this spot. So you can see that our blocks are falling down the screen, but they're stacking on top of each other and we're not able to do anything to manipulate them as they're falling down. Let's start off by adding some keyboard commands so that we can move these guys left and right and so that we can spin them around as they're falling. So I'm inside the block sprite where most of the game is located, and we're going to work on a when left arrow key is pressed event here. So when the left arrow key is pressed, we're going to move one square over to the left. You'll remember our squares are 20 pixels in size. So we're going to change our X by -20, and that will move us over one slot. Now, there's a couple of circumstances where we don't want to be able to move left, and one is if we hit the edge of the screen here. And the other situation is if we have a block that we're going to smash into. So if we move 20 pixels and we end up on top of a different colored block, we're also going to want to disable that movement and make it not happen. So because things happen very, very quickly in Scratch here when we don't put any time delay in, we're going to move quickly left and then we'll be able to change our mind if the circumstances aren't right. And it will all happen so quickly that you won't even realize it. So now that we're 20 pixels to the left, we're going to do a little quick color check to see if we're overlapping on top of any of the colors that will tell us we're in the wrong place. So we're going to grab some of these sensing blocks that are saying touching a certain color here. So if we're touching a color, now we don't want to estimate this. The color has to be dead on with the color that we're going to use, that we're actually going to collide with. If any of these color values here are even one off, then the detection is going to mess up here. And that's why we're going to use this little eyedropper tool to pick our color. And let's go over and zoom in really close to this. So the first thing we want to detect here is if we're touching this left-hand wall here. So I'm going to grab the color of the left-hand wall here and click, and that's going to input our values here, which will give us a color of 50, a saturation of 21, and a brightness of 100. And again, those colors have to be exact or the detection isn't going to work. All right, we're going to grab a second color here. So if we're on top of another block, they might be of different colors here, and we don't want to do a complex check here where we're checking for a bunch of different colors. So what I'm going to detect here instead with my eyedropper tool is the color of the edge of the squares, this gray color here, and we're going to grab that and use that as our collision detection here. All right, so we're checking for those two different blocks. If we're superimposed on top of either of those colors, then we're going to move back. We're going to change our X by 20, and that will make it as though we weren't able to move at all. Okay, let's go ahead and test that. You can see that when I try to move this pink block too far, it's just not letting me. And let's go ahead and grab this blue block and wait for it to go beside the pink, and then we'll try to push it on top of the pink block. And again, no joy, and it just stuck there in that spot. Okay, that's perfect. So you can probably guess that the same process is at work with our right arrow key is pressed, except we're going to be moving in different directions. So we're going to move by +20 when we're going to the right, unless we've gone too far, and then we're going to go backwards -20. Let's give that a look now. And you can see that now I'm moving left and right, but again, I'm unable to move off the side of the screen. So that's just working perfectly now. The down arrow is actually surprisingly simple to code because we already have a block that manually moves our objects down the screen by one square, and that's called check position. It's a custom block that we set up last week. And so every time this block is invoked, you can see here that a block goes down one step and then checks to see if it's reached the bottom of the screen or has collided with something, basically. So that's all good to go. We just need to make sure that we can't manually push these guys down if we're in a position where the block is already locked into place. So we're going to grab an if statement and say if lock is equal to 0, then we're going to allow ourselves to check position. And so now that this is implemented, we can speed up the gameplay a little bit. Once we're sure that a block is in the right spot, we'll be able to hit the down button and rush it down to the bottom of the screen, which is going to save us the trouble of having to wait for it to slowly make its way down the screen. So the up arrow, which will rotate our blocks around, is a little bit more complicated, mostly because spinning around can get us into some trouble overlapping with different blocks, or maybe even pulling us right off the edge of the screen if we're not careful. So we're going to implement a few things to check and make sure that rotating isn't going to take us in the wrong direction. First, let's do the actual spin though. So when the up arrow is pressed, we've got a variable called I here. There's a couple of spots where we're going to be manipulating it. I is usually just used as a counter in programming. So we're trying to keep a tally of how often something has happened. So this will already be at 0 by the time we get to the place where we're playing here, and we're going to change it by 1. So the first time we spin around, it's going to be 1, and then the next time we spin, it'll change to 2, etc. as we're coming down the screen. So we're going to reset this. If we reach 4 by changing this by 1, then we're going to go back down to 0, and this will just get us going in an endless loop where our costume will always be 0, 1, 2, or 3. And at that point, we're going to do a switch costume. When we're going to switch to costume number, remember we saved the costume we were wearing, and then we're going to add that number I to it. So if our costume number is 5, for example, then we're going to change to costume number 5 plus 0 if our I is 0. And if we, as soon as we switch to the next costume, it's going to go to 5 plus 1, which is costume 6 here, etc. Now the square is probably not a good example because it doesn't actually look like it's spinning no matter what costume it's wearing. But here in this wide block here, for example, you can see that when we spin it the first time, it'll do this. And then the I will be equal to 2, and then finally to 3 when it comes around this way. All right, so that's all that it takes to spin it. As I said, the rest of this code is all about error correcting and making sure. So let's run the program right now. And so you can see that I'm able to spin this block around. But if I move it right next to the wall here, if I spin it, it will occasionally end up embedded inside the wall. And we don't want that, of course, because it's assuming that it's reached the bottom of the screen now, and it's freezing those guys in position. Let's try this guy on the right here, and you can see the same situation happens. So we need this guy to bounce back if he ends up touching a wall or touching another sprite, and have him kind of boing back to the middle again or towards the center. So that depends to a certain extent on whether we're going to the left or to the right side of the screen here. So in addition to knowing which direction we're facing, we have to pay attention to where our walls are here. And that's why we've got some if statements here that are checking to see whether our X position is less than or greater than 0. And so what these blocks are doing is saying if I'm on the left side of the screen, if my X position is less than 0, which is the middle of the screen, that means I'm over on this side, and that means I've probably bumped into a left-hand wall. So if I've done that and I'm touching color blue, which is the color of this wall area, or if I'm touching another block that's to my left, I'm going to bounce back to the right, and we're going to do that by 40 pixels here. And so more than one block, we just want it far enough away that there's no chance at all that it could end up colliding with one of these other blocks. We're going to do the same thing on the left, except on the right hand side, except have the block move left if it collides with anything. Now there's a couple more checks. If we end up on the bottom of the screen, which means that we've passed both these checks and we're not touching a wall, but we're still touching blue, that must mean we're touching the floor, and then we have to pop ourselves back up again. So we're going to change our Y by 20. And one last series of checks here, and these are assuming that I haven't touched a wall and I'm still ending up touching a neighboring block, which is a gray one here. Then we're deep in muck here, and we're gonna have to move it back by 60 just to be sure that we're still not on top of something. So this block probably won't be used very often, these two blocks here, but they're there. I believe that Wang probably put them in here because there were a few weird circumstances where the blocks were still overlapping even after these other checks had been made. So let's go ahead and put those in there. And that is really all we have to do to be able to safely spin these guys around. Let's give this a try here. And now we can fully navigate these blocks around the screen without accidentally doing anything to mess them up. So here's an example where it would overlap, and you can see that no matter what I do, I can't make it overlap across the edge of the screen. All right, let's put this guy down just right next to it, perhaps. And let's put this guy on top of it so that we can try to do some more collisions here. All right, so this guy here, I'm going to turn him vertical and then try, yeah. So you can see that no matter what I try to do here, I cannot overlap these guys on top of each other as they're landing. And they're spinning quite nicely. Okay, so the main thing I wanted to teach you today was how to erase these blocks. You'll remember that in Tetris, when we finish an entire row of blocks here, we want to be able to delete it and move everything down. Now that again isn't a very obvious thing to do. We can't break up these sprites. We've turned them into backgrounds, but now do we need to store all of this information and then transpose it all down one level? I mean, that is an approach that we could use. We could create a gigantic list to store the color of these blocks in every single square and then find a way to transpose it down a little bit further. But Wang, my co-op student who produced this game, had a brilliant system of his own for how to do this that is far simpler, deceptively simple, and I'm going to show that to you right now. So we're inside the blocks sprite where we have this custom block called check position, and it is basically just moving the blocks down the screen, making sure that we're not colliding with the bottom of the screen here, and moving it up if we end up going too far or if we overlap on an existing sprite. Now, last week we took the broadcast new block, the part that actually starts the next block going after the first block is locked into place. We took it and put it here into check position, but I did leave a little note here to remind us that this isn't its permanent home. We just wanted to get the game working at this point. This is going over to the tile sprite now, and we're going to be doing some work over there in a couple of minutes. So let's remove that, and we're going to add a new broadcast here. So if it is colliding with something here, in addition to stamping the block, now we need to check and see whether we've finished building an entire row of blocks. So as I said, we're going to do that over in a different sprite. So let's just go ahead and broadcast that message now. So that message is going to be called check line. And that will be received by another sprite here that we haven't looked at yet, and that is called, surprisingly enough, check line. Let's go have a look at that sprite. So this is a bunch of dots in bitmap mode. They're colored blue. And there's one of them here for every single one of the squares in a row of Tetris here. Let me show this, and you can see that it's right here at the top of the screen here, and as I bring it down. So if we superimpose this on top of an existing square, you'll be able to see that we'll be able to check collisions across the entire row. And the idea is going to be that if this sprite in any way is touching the color black, you will know for sure that there is an incomplete row here. And if it's not touching black, that means we'll have finished that row and we can move it down. So a very clever detection system here, that instead of having to check these one block at a time, we can check an entire row at a time to see if it's complete. So that's very, very clever. Let's go have a look at the code for this. So when I receive check line, we're going to want to take this block and move it down to the first row, and that's what 0 minus 150 is. That's the bottom row of this playing area here. So we're going to start at the bottom row. We're going to make this ghost effective 99, and you guys who've been with me for a while will know that a ghost effective 99 is a common hack that we use to make something transparent but still be able to do checks on it, like collision detection and color detection. So even though it won't be visible to us at a ghost effective 99, it'll still be interactive with the rest of the blocks on the screen here. So we're going to show it so we can start doing some color checks here. We're setting a variable called line count here, and that line count is the which of these rows we're looking at. We're going to look at the first row, and then if nothing is successful here in our search, we're going to go to the next and the next, and we're going to continue to scan the whole screen. And you'll remember the screen is actually 17 rows deep here. So that's why we've done a repeat 17 here. So we're going to start checking for that color black now to see whether our rows are complete. We're going to do it in the if-else statement. So if we do find black, which means we have an incomplete row, then we are going to just check the next row. We're just going to ignore this row and move along here. So we're going to change our Y by 20, which is going to move our detector up one row so we can start looking at the next row the next time around our loop. We want to keep track of that line count, so we want to know that we're in line 2 next time. So we're going to change that line count by 1, and that will keep track of how many rows we've gotten to here before we actually find a row with no colors, with no black in it. Okay, so if we do find a row with no black, a completed row, we're going to have to do a couple of things here. The first thing we're going to have to do is we're going to broadcast a message that says delete line and wait. So we're going to jump over to another event received here, and that's where we're going to run the routine that's actually going to delete that row and bring everything else down by 1. I'm going to show you that in a second, but while we're in here, let's just finish up this block of code. So if that does happen, we'll successfully delete that row, then we'll change our line number by 1, and we'll keep checking because there might be other completed rows above that one. You can't complete more than one line at once, so we definitely don't want to stop yet here. All right, and then we're going to change our score. So if we successfully delete a row, that's the objective of the game, of course. So we're going to change our score in here. We're going to change it in a way that when the game gets harder towards the end, we're going to get a higher score the longer we survive. So we're going to take the level. Right now we're on level 0. We're going to add 1 to it so we get at least 1 point of score, and we're going to multiply that by 40. So on level 1 we'll get 40 points, and on level 2 we'll get 80 points, etc. Moving up as the game gets more difficult, our score will start to get higher. All right, once all this detecting is done, we're just going to hide this sprite again, and then we're going to broadcast that new block. So here our new block, which we moved over from the block sprite, is here, and that's going to keep the game going. Okay, so let's move on to the actual delete line code. So the code is frozen here, waiting for us to delete that line before we go on and go around this loop one more time to start detecting. So we're back inside the tile sprite, the little black square that we've been using to detect whether we're overlapping an existing square, and then we've been changing the color and stamping this down. So we're going to use this same tool to shift blocks down and replace them with the proper colors that they should be once everything is moved down one level. And as I mentioned, Wang has come up with a very creative way to shift these blocks down without having to store the location of all these blocks right now. So let's get into that. So when this delete line message is received, we're just going to want to play a little sound effect to let us know what happened. And this is a default Scratch sound called oops. There we go. Then we're going to move down to the bottom right of the screen, which is at 90 minus 150, to the bottom right hand corner where we were the last time when we were trying to start scanning across the screen. So we're going to switch costume to costume 1, the black costume. And we're going to make sure we're at the front here so that we're in front of anything else that might be interfering with our measurements here. And now we don't necessarily want to be in the first row, though. We want to be in the row that was affected here. So that's where that line count variable goes in. We're going to change our y by the line count, which is what row we're in here, times 20, because each row is 20 pixels high and wide, of course. So we're going to move up to the proper row, and then we're going to start scanning to the left to see what's there. So that's all going to be inside a custom block. Once again, we have to do it inside a custom block because this process is very time consuming. And when things are inside a custom block, we can tick on this little block here that says run without screen refresh, and that will dramatically speed up the process of evaluation. It'll do all the math quickly without having to worry about what's on the screen at any given time. And so that's gonna, by orders of magnitude, speed up this shift line process so that we don't have to sit around waiting for it to be done. So let's go over and have a closer look at this shift line block. You're gonna see a lot of similarity with the stamp custom block that we completed back in episode 1 of this tutorial. You're seeing we're going through a series of if-else statements where we're checking to see what is the color underneath this black tile sprite. What is it detecting? If it detects purple, then it switches costume to match it. If it detects yellow, it switches costume to match that, and keeps going through all the different potential colors until finally it should have switched to one of those colors or just to black. And so in the case of the original block here, the one that we did yesterday, what we're doing is actually just taking the clone and stamping it down in its original position. What we're doing differently here, though, as you can see, is once we identify that color, the next step is that we're going down 1 square. So we're taking the existing color, well, whatever it is that we find underneath our cursor, and we're bringing it down 1 square and then stamping it. And then we jump to the left to the next square and move back up to the original line and then sample from that line. And so we're just, instead of having to memorize this entire grid and move it all down at once, we're just looking at the square right above us and moving it down, and then moving to the next square, looking above us, moving it down. And that way, 1 square at a time, we're bringing the entire grid down 1 square. Just think it's a really, really smart technique. Now, the other bit of code here that you should be aware of is the repeat loop is a little bit different here from the original stamp loop as well. And that's because depending on how high we are when we want to bring this layer down, we don't want to do this 17 times. If we're up on the 4th layer, we only need to do this 13 times. And so to avoid having to run this loop more times than we need to, we're only going to run it the number of times that's 17 minus the number of lines that we've already done. So this is another one of those blocks that I'm just going to give you. It's a little bit too finicky, and I have no doubt you'd be able to duplicate this, but it's just going to take a lot of unnecessary time and effort, and it's just going to frustrate you. So both these files here, the stamp and the shift line, are going to be available in the starter file and also in all the catch-up files that I give you, so that you don't actually have to code this yourselves. Okay, one little detail I forgot, which is after we're done shifting line, when we return back to this part of the code here, we do want to hide this object so that it's not covering anything up on the screen, and it'll be sitting there waiting for the next time around. Okay, we are ready to test this code out now. Let's play a round of the game. So I'm going to fast forward this process for a couple of seconds until we can get a row ready to delete itself. All right, here comes a square, which is going to be able to delete that bottom row. And so let's watch that process now. And you can see that we completely removed that row. And let's do it one more time here. Yes. And you can see that tall block is now 3 high instead of 4 high. And so this is working beautifully. So we're very close to having a functional game here. Just a few little details to clean up. Firstly, we need a game over event to make sure we don't play this forever. And we need the game to get progressively harder as we play it. Now, both those functions are contained inside this falling custom block inside the block sprite. So let's go ahead and make those little updates right now. I mentioned earlier that there's a set I to 0 variable that's set earlier in the process, and this is where we want it actually. So right underneath your custom block here, let's put set I to 0. That'll initialize this before we start spinning our blocks around, and we need to keep track of the costumes. All right, so the game over event we could put before we start moving stuff down. We're going to be placing a new block, and if we're placing a new block and it's immediately on top of another block, you'll know that our blocks have stacked up to the top of the screen or a game will be over. So all we're going to do here is we're going to say if touching that color gray, the edge color around these blocks, then we're going to broadcast a game over, and we're going to stop all the blocks from falling. So we're going to stop this script, and that will cease the forward motion of all these blocks in the game. And in the meantime, we'll have a game over appear on the screen. There is a sprite here called game over, and the coding on it is pretty straightforward. It's just show when we get to a game over event and hide otherwise when other stuff is going on in the game here. And we're going to put a restart button in here too. Wang has drawn a little simple restart button. We're going to superimpose that on top of that game over message right down here at the bottom of the black square. And we're going to do a little what's called a rollover effect to make it get a little bit bigger when we hover our mouse over it and a little bit smaller when we move our mouse away. And that'll give us a little visual cue to let us know that that this is a pressable button. Let me just show you the code quickly. There's not a whole lot to this. So we're just going to send it to a position here just a little bit below at y minus 26. You'll remember the game over was at 0, 0 right in the middle of the screen. And we're just going to be constantly checking if we're touching the mouse pointer. So if we are, we'll set the size to 110, and we'll bump up the brightness of the image a little bit. And Wang has put two different if statements here. I think this should probably be an if else, so I'm going to call an audible here and make it change. And we're just going to set the size back to 100% here, and then set the brightness effect back to the default to 0 when this happens. So if we make this all appear here, you can see that once we trigger this game over event, we get a nice little rollover effect here that will tell us to click that button. And when we click the button, when this sprite is clicked, we're going to hide all this stuff again and broadcast getting ready, which is just going to get us right back into the game again. There's just some initialization code here that hides this stuff at the beginning. I think that's pretty well all there is to that part of it. So back inside the falling block again, as I said, we do want the game to get harder as it carries on here. So we've got a little bit more code that relates to that. And I'm going to just plunk that in here and explain it to you bit by bit. So this if statement, so we're counting which line we're on as we're evaluating these blocks. And so it's saying here if our line is greater than 0 and our line mod 10 is equal to 0. So what we really want to do is we want to check every 10th time that we complete a row here. Our line number, the number of lines we've completed, is going to go up. And we're going to go to the next level of the game. So every time we delete 10 rows, we're going to go to the next level. And so what we're saying here is we don't want that happening the first time around. So we're going to have it go every time that this line number equals 0, except for the first time, we're going to make the timing of the falling blocks change. And so this line mod 10, we've used mod before in a couple of other projects, but mod 10 basically takes any huge number that's increasing, and it makes it so that when it gets above the mod number, so the line number is going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then once it hits 10, and is with this mod command, it's going to go back down to 0. So the mod basically lets a number never get past that mod number, and it'll just go right back down to 0 again. It's a great way to do loops and stuff in coding, where we want stuff to count up, and then when it gets to a certain number, it goes back down to 0 again. And so this is just checking to see if we've reached the 10th level or the 20th level or the 30th level. It's just going to keep checking every 10 levels, and that number is going to hit 0 after it's modified at that point. And then we'll know that it's time to ramp up the difficulty of the game. How are we ramping up the difficulty? Well, so we're just going to make the time pass faster. This time variable is happening every time that we move our blocks down. We do a little pause here before we do it again. And so that started off at 0.8 seconds, and then we're going to multiply it by a factor here that's going to make it smaller, 0.95. Now I think Wang is making this game get difficult a little bit too slowly, and people might find it a little frustrating that they're playing for a long time. So if you want the game to be more difficult, you'll want to decrease this time by a smaller number here, multiplying by 0.8, 0.7, 0.6 or something along those lines, and that will make the time pass much more quickly and the game accelerate its difficulty level faster. And every time that we do make that go up, we're going to change that level marker by 1. All right, let's go ahead and simulate a game over, just so that we can show you how this is all going to work in the final analysis. Alright, so we're going to put a block down here and try to put a block on top of that. And there was a purple block tried to go on top of the light blue block, and they overlapped, and that created a game over event. So that's perfect. Now when we click our restart button here, I have discovered a little error that I inserted in the code earlier that we're going to have to fix to get that running again. So inside the tile sprite here, we've got an event called Getting Ready that resets the game, and I put the erase all underneath the green flag here, when in fact it should be under the Getting Ready. Just to be safe here, I'll put it in both places. There we go, and now when we go back to the game again, you'll see that that fixes that glitch, and our game has restarted itself again. All right, so we are in excellent shape here. So the part that's not ready is just really gloss that we want to add to the game. You can see all of these areas here: top score, score, level, lines, statistics. There should be numbers here, and this is what we're going to add in next week's session. So we're going to create a system where we're interpreting these graphical number blocks here and turning them into screen numbers that conform with what's happening in the game here. I did a whole other mini lesson on how to do this stuff a few weeks ago, but in the context of this game, I'd like to show you all the details because there are some wrinkles to it. So we'll be teaching you how to do that part next week in the third and final part of this tutorial series. Hope you're having fun. If you like this video, please like and subscribe and leave comments and do all those other things that make the YouTube algorithm like me. I'm hearing a lot of people saying that I'm an underrated YouTuber, so if you want to see me do better, then I'm going to need your help. In the meantime, happy scratching, everybody, and we'll see you next week for part 3. This tutorial was produced by Chromeworks Technology. For more Scratch tips, tutorials, game reviews, and interviews, subscribe to this channel and make sure to tune in to our weekly live show, Saturdays at 10 a.m. Eastern on YouTube.